Hello and welcome back. We're almost done with this section, just a couple more notes, a couple more examples, and we'll be good to go. The first note is that sometimes we can be lazy with our sigma notation. Technically, you would want to write the sum as n goes from 1 to infinity of a sub n, but if you drop the n equals 1 to infinity, it's implied. It's kind of like dropping the 1 up there in the exponent, or the 1 coefficient. You don't really need to write it, you know it's there, and that's okay. So if you just see me writing something like this, the sum of a sub n, it's implied that n starts at 1 and goes to infinity. And we're going to use that for the second note here. So suppose you have a series a sub n and a series b sub n that both converge, then these two properties apply. The first property basically says that the summation distributes across addition and subtraction. The only catch is that each of these individual series would have to converge for you to be able to take this step. So you can only take this step when the two individual series converge. The other property is that a constant coefficient can be pulled out of the series. This is like factoring a constant from every single term of the series, because here k is a factor of every single term of the series, so you should be able to factor it out of every single term of the series, and that's all we're doing in this step. Example 7 will be a case where we can use these two properties. And here I explicitly wrote n equals 1 to infinity, but we don't have to necessarily write that. So let's get practice being lazy. Here we have the sum of 3 to the n plus 2 to the n all over 5 to the n. Now one thing we could do is we could break up the fraction into two little fractions. This is going to be 3 to the n over 5 to the n plus 2 to the n over 5 to the n. Now we can break this up into two separate series. This will be the sum of 3 to the n over 5 to the n, excuse me, plus the sum of 2 to the n over 5 to the n. Now we can only do this if the individual series converge. So if we find that one of them diverges or both of them diverge, well then we don't really know what's going to happen with the original series that we started from. It could converge, it could diverge, we're not exactly sure what's going to happen with that. But if both of these series individually converge, then we know that the original series has to converge as well. Okay, so one way we can take a next step here is by rewriting this as 3/5 to the n. This is the same thing, it's just an exponent property that can get you from one to the other inside. Similarly, this is 2 over 5 to the n. And these two series are looking like what kind of series? What kind of series have we learned about that looks like these two series? Something to the nth power. Geometric series, right? This is a geometric series in form. If you wrote out the terms of the first, it would look like this. Remember that the default is n starts at 1. So when n equals 1, you get 3/5. When n equals 2, you get 3/5 squared, which is 9/25. When n equals 3, you've got 27 over 125. Every single time you're multiplying by, every single time n increases by 1, you're multiplying by another 3/5. So this is a geometric series. It's a geometric series with a equals the first term, which is 3/5. R equals the common ratio. That's the thing that you're multiplying by to get the next term, which is also 3/5. And in a similar way, the second series is a geometric series. Here, the first term is going to be 2/5, and the common ratio will be 2/5. Now we talked about formulas for determining, or a heuristic for determining whether or not a geometric series converges or diverges. We said that if r is between -1 and 1, it converges. And that's what is happening with these r's. These r's are between -1 and 1. They're proper fractions. So both of these series are going to converge, and they're going to converge to a over 1 minus r. That's what we figured out. So we have 3/5 over 1 minus 3/5. And 2/5 over 1 minus 2/5. Now here I'm going to avoid some of the fraction work. I'm going to write just this turns out to give you 3 halves plus 2 thirds, which gives you 13 over 6. Just blast past that. And that's what this infinite summation adds up to. It adds up to 13 sixths, which means that it converges to 13 sixths. Sixths is a really hard word to say, I have to say. I wish they could replace it with something else. All right, so it converges. Notice that we were using these summation properties while we were doing this. We didn't use the second one, but we used the first one at least. Example 8 will give us an example to work with the second property. So here we have the sum as n goes from 1 to infinity of 4 over 2 to the n. Does that one converge or diverge? Well, the first thing we could do is factor out the 4 from everything. And we're left with 1 over 2 to the n. 1 over 2 to the n can be written as 1/2 to the n. And again, it's a geometric series with a equals 1/2 and r equals 1/2 in a very similar way to example 7. I'll write geometric. So this will converge to a over 1 minus r, 1/2 over 1 minus 1/2. And if you work that out, you get 1/2 over 1/2, which is 1, so you just get 4 times 1, which is 4. In other words, this series converges to 4. Okay, so that concludes this section. Thanks so much for watching these videos, and see you next time.